Hello everyone, I'm Dimitri and today I came here to share about a cute little function that I learned a couple months ago, and it is sine 1 over x. And before introducing the function and interesting limits of it, I want to thank everyone. Thank you for allowing the Thinking Tree channel to have 102 subscribers. Thank you so much for your help and assistance. I'll work harder to create a better and fun videos. About the topic, I'm actually planning to divide this topic into 3 different videos because I want to explain this into 3 different ways. And I actually wanted to make it as one video, but it will be too long. I thought dividing might be more effective. So it will be divided into 3 parts. The first one, second one, and third one. The first one is what we are going to do today, explaining the limit of sine 1 over x as x approaches 0 using limits property. And by the way, if you're planning to leave right now, please stay because I'm going to briefly explain what limit is, just in case you might not be familiar with limits. And the second one is using the graph of sine 1 over x. I'll visually explain it. And I actually like the last one. Last one is using Epsilon-Delta proof. Epsilon-Delta proof is quite hard to understand. It took me a couple days to understand Epsilon-Delta definition of limits and examples using the Epsilon-Delta proof. But today, you'll be very intuitive using limits property. So let's start. So first, to use limits property, I will very simply describe what limits is. So what limit is saying is that what is y here? It's x. Let's say there is a function that looks like this, y equals f of x. And let's say this point is a and this point is fa. Then now I can write this as the limit of f of x, as x approaches 0, a is equal to fa. So the limit of f of x as x approaches a is equal to f of a. Now, to explain why this is the case, we need to think about the continuity, and there might be topic for different videos. And this is just a very intuitive explanation. So just think about it. As x approaches a closer and closer to a, as x is approaching, we're closer and closer to a. In Korean textbooks, you will see arrows like this. Very cute arrows like this. Oh, that's not visible. As x approaches a, the y value is approaching f of a, right? That's all. Yes, there's nothing more. No, just kidding. There is a proof that you can use, which is Epsilon-Delta proof. And I'm going to use that in my third video about this topic, so stay tuned. I can say as x approaches really close and closer and closer to 0, so I'll just write it. As x approaches 0, this one, it is approaching infinity, right? As x approaches 0, 1 over x is approaching infinity. Now then, can I just say that in this case, the limits of x sine x as x approaches infinity? Because when you just think about it, This is saying that what is the limit of sine x as x approaches infinity? So what is happening to the sine graph as the value that you're plugging in is getting bigger and bigger and bigger? So when you plug in 1, it's 1. 0.1, it becomes 10. 0.01, 100. 0.001, it becomes 1000. So it is just basically asking you, what is happening to the y value of sine function as the value that we are plugging in is getting bigger and bigger? And this one is basically saying that what is the limit of sine x as x approaches infinity? So these two have different forms and how they approach. Their ways of approaching the limit is different, but the whole concept is the same. They're leading to the same conclusion. And now I will briefly explain this. So let's say there is a long sine graph. We usually only draw these four parts when solving problems, but it's to demonstrate the limits. So the graph looks like this. Sine function is a very cute function that has periods, so it is just repeating this, repeating, and keep repeating like this. Isn't this very cute? And there is a reason why I say it's beautiful. First of all, it has periods. So sine function is keep repeating this part. It's keep repeating. Isn't it just so pretty? So there are countless number of this period, and the length of the period is only 2 pi. And also, there is the maximum value, which is 1, and the minimum value, which is -1. Also, this function is differentiable and continuous on every point. Can there be more perfect function than sine x? I mean, I love other polynomials. They are easy to deal with too, but I think sine x is very beautiful function. Anyways, to get back to the topic, so what is happening to sine x as x is approaching infinity? So I say, okay, let x is getting bigger and bigger and bigger. It is approaching 1. No, it is approaching 0. Wait, I think it's -1. Isn't it 0 again? No, I think it's 1. No, 0. No, -0.5. No, -1, 0. Then what is the limit? Well, simple answer, it does not exist. Simple reason, it's oscillating. Yes, the function is oscillating. So basically, in simple way, what y value is it approaching when x is getting bigger and bigger? There's no certain y value, right? So we don't know. It does not exist. Since the limit of sine x as x approaches infinity does not exist because the function is oscillating, the limit of sine 1 over x as x approaches 0 also does not exist. They're saying the same thing. Thank you so much for watching this video, and if you want to see the next visual proof, please stay tuned. And also, if you want to check out my Epsilon-Delta proof for this limit, please don't forget to subscribe and like the videos, and see you later.